All right, so you send us this YouTube video, What are the Hidden Rules of the Universe, from the channel History of the Universe. And it dives into some seriously cool stuff like symmetries and antimatter, and even touches on the possibility of other intelligent life.
Right.
And we're going to unpack it all for you today.
It's amazing how these concepts are all interconnected, really.
Yeah.
The video explores some of the most fundamental ideas in physics and how they link everything from the shapes we see in nature to the forces that govern the universe.
Exactly. It starts off with this wild scenario where two advanced civilizations finally meet after, being light years apart.
Okay.
They've exchanged knowledge. Their science seems to match up. Everything's looking good for a first contact situation.
It seems like it would be a monumental moment of unity, right? But here's the catch. One civilization is made entirely of matter and the other antimatter. The moment they touch, total annihilation.
Okay, that's definitely a twist. But wouldn't their understanding of physics have tipped them off beforehand?
Mm-hmm.
I mean, how could they miss such a crucial difference?
That's exactly the point the video raises. The distinction between matter and antimatter isn't always obvious. It's often hidden within the deeper, more subtle rules of the universe. One of those fundamental rules is symmetry.
Symmetry, like how a butterfly's wings are mirror images.
Exactly.
I get that we see it everywhere in nature, even in art and architecture.
Exactly. The video even mentions the Taj Mahal and Da Vinci's Last Supper as examples. But symmetry's significance goes way beyond aesthetics. It plays a crucial role in mathematics, and believe it or not, even modern cryptography.
Cryptography? Really? I never would have connected those two. Tell me more about that.
Well, the video brings up mathematician Évariste Galois, who had this groundbreaking idea. He connected symmetries to solutions in algebraic equations. That work led to something called group theory, which, as it turns out, has unexpected applications in creating secure encryption algorithms.
So, like, the symmetry inherent in mathematical structures helps keep our online information safe. That's fascinating. But how does this all tie back to the universe and its so-called hidden rules?
Think of it this way. The universe operates on certain principles, much like the mathematical structures Galois studied. One of these principles is the principle of least action, which basically means the universe tends to take the most efficient path, the one that requires the least amount of effort. The video uses an analogy of a rescuer on the beach trying to save a drowning person.
Okay, I'm picturing it. The rescuer sees someone in trouble, but instead of running straight into the water, they run along the beach for a bit first, even though that might seem longer.
Exactly. The rescuer instinctively chooses the path that minimizes the time spent swimming, even if it means running a longer distance on land. It's the fastest, most efficient way to reach the person in need.
So they're optimizing their route, not just blindly charging in. That makes sense. But how does a rescuer on a beach translate to, the entire universe?
It's about recognizing the underlying principle. The universe, like the rescuer, also seeks the most efficient path. This isn't just some whimsical idea. It's deeply embedded in the mathematics of physics, thanks to the work of physicists like Lagrange and Hamilton.
So you're telling me the universe is basically a master of efficiency, always taking the shortcut.
Pretty much.
That's pretty cool. But where does the hidden rules part come in?
Here's where it gets interesting. This laziness of the universe, this principle of least action, has a profound consequence: conserved quantity. And that's where Noether comes in.
Another famous mathematician. Didn't she make some big discovery about symmetry?
She absolutely did. Noether's theorem states that every symmetry in the laws of physics leads to a conserved quantity, meaning something that remains constant. For example, you've probably heard the saying, energy cannot be created or destroyed, only transformed.
Yeah, like how solar panels convert light energy from the sun into electricity.
Exactly. The conservation of energy is a direct result of the fact that the laws of physics are symmetrical in time. No matter when you conduct an experiment today or tomorrow, the results should be the same, because the underlying laws governing the experiment don't change with time.
So because the laws of physics are consistent over time, we get this fundamental principle of energy conservation. It's like a hidden consequence of time symmetry.
Precisely. And there are other conserved quantities like momentum and electric charge, each stemming from different types of symmetries. But what happens when these symmetries are broken? That's where things get really interesting.
Broken symmetries, does that have something to do with the matter and antimatter civilizations from the beginning of the video?
You're on the right track. Let's go back to that concept of parity, the idea that the laws of physics should be the same in a mirror universe. For a long time, physicists believed this to be true. But then Qiansheng Wu conducted an experiment with spinning cobalt atoms. And, well, let's just say she threw a wrench into things.
Okay, a wrench?
Yeah.
Sounds ominous. What did Qiansheng Wu discover that shook things up so much?
Her experiment showed that the weak nuclear force, one of the 4 fundamental forces of nature, actually violates parity. It doesn't behave the same way in a mirrored situation.
Wait, so the universe doesn't always follow its own mirror image? That's kind of blowing my mind right now. What does that even mean for physics?
It means the universe has a preference. It inherently distinguishes between left and right, something we never expected. And it's all because of this weak force.
So how does this tie back to those matter and antimatter civilizations? Would they have been able to figure out they were made of opposite stuff if they knew about this?
Absolutely. If they had studied the weak force in detail, they would have seen that it acts differently on matter and antimatter. It's a concept known as CP violation.
CP violation. So even if you flipped both the charge A and D, mirrored the scenario, things still wouldn't line up perfectly.
Exactly. And this seemingly small difference has huge implications for the evolution of the universe, especially when we consider the matter-antimatter imbalance.
Okay, I'm really curious about that. I remember from the video that in the early universe, there should have been equal amounts of matter and antimatter, right?
That's what we'd expect based on our understanding of symmetry. Imagine the early universe, incredibly hot and dense, with a single unified superforce. It was a state of perfect symmetry.
So everything was essentially the same at the very beginning. No distinction between forces or particles.
Right, but as the universe expanded and cooled, those symmetries started to break down. It's kind of like water freezing into ice, a phase transition that fundamentally changes how things behave.
So as the universe cooled, those perfectly symmetrical conditions couldn't hold anymore, and that's how we got the four fundamental forces we see today.
Exactly. Each broken symmetry led to a separation of forces. First, gravity split off, then the strong and weak forces, and finally, electromagnetism.
It's amazing to think that the universe went from this unified state to the complex tapestry of forces and particles we see today, all because of these broken symmetries.
It really is. But there's another piece to this puzzle that the video touches on: magnetic monopoles.
Magnetic monopoles. Refresh my memory. What were those?
They're hypothetical particles predicted by the symmetry of electromagnetism, but we've never actually observed.
So they're like the missing link in electromagnetism.
In a way, yes. And their absence has puzzled physicists for a long time.
Did the video offer any explanation for this magnetic monopole mystery?
It brought up the theory of inflation, which suggests that the early universe went through a period of extremely rapid expansion. Imagine blowing up a balloon really, really fast. Any markings on the balloon's surface would get spread out so much that they'd become incredibly difficult to detect.
So inflation stretched the universe so dramatically that any magnetic monopoles that might have existed are now just spread out too thinly for us to find.
Precisely. It's an elegant solution to the monopole.
Okay, that makes sense. But what about the matter-antimatter imbalance? Inflation explains why we don't see monopoles, but it doesn't explain why there's so much more matter than antimatter.
You're right. And that's where the mystery of baryogenesis comes in. It's the era when the matter we see around us was created. The decay of the influent field, the force behind inflation, likely reheated the universe, providing the energy for particle creation.
But even with that energy shouldn't matter, and antimatter have been created in equal amounts, canceling each other out.
In theory, yes. But that's not what we observe. The universe is dominated by matter.
So something must have happened to tip the scales in favor of matter.
That's the big question. Even the CP violation we talked about, which shows a difference between matter and antimatter, isn't enough to explain the huge discrepancy we see today.
It's like we're missing a piece of the puzzle. Is there anything in the video that might point us in the right direction?
The video suggests that there might be other asymmetries, other broken symmetries that we haven't discovered yet. These hidden rules could be the key to understanding why the universe is the way it is.
So there could be more to the story, more layers of complexity that we haven't even begun to uncover. That's both exciting and a little daunting, isn't it?
Absolutely. The quest to understand the universe is never ending, and that's what makes it so captivating.
It makes you wonder what these undiscovered asymmetries might look like and what kind of impact they could have on our understanding of the universe. Does the video offer any clues?
Well, it briefly mentions the idea of supersymmetry, which some physicists believe could hold the answers to some of the biggest mysteries in cosmology.
Supersymmetry. That sounds intriguing. What's the basic idea behind it?
It proposes that for every known particle, there's a partner particle, a sparticle, with slightly different property. It's a bit like a mirror image, but at a deeper, more fundamental level.
So like every electron has a selectron, every quark has a squark, kind of like a secret world of particle dots.
That's a fun way to think about it. And if supersymmetry is correct, these particles could help explain things like dark matter, which we know exists, but haven't been able to directly detect.
So these particles, they're like the cosmic ninjas of the particle, hiding in plain sight, but potentially holding the key to understanding some of the universe's biggest secrets.
Exactly. But finding them has proven to be incredibly challenging. Even with the Large Hadron Collider, the most powerful particle accelerator ever built, we haven't seen any direct evidence of supersymmetry.
So does that mean supersymmetry is wrong? Or are we just not looking in the right place?
It's hard to say for sure. It's possible that these particles exist at energy levels beyond our current reach, or that they interact with ordinary matter in ways we haven't anticipated yet.
So the search continues. It's like a cosmic treasure hunt with physicists as the explorers and these elusive sparticles as the hidden gems.
It's a fantastic analogy, and the stakes are incredibly high. If we find evidence of supersymmetry, it would revolutionize our understanding of the universe.
Yeah.
It would mean that there's a whole other level of reality governed by these deeper symmetries just waiting to be discovered.
It's mind-boggling to think that we might just be scratching the surface of what's really out there. But let's zoom out for a second. We've covered a lot of ground dive. From butterflies to black holes, from ancient mathematicians to cutting-edge physics. What do you think is the biggest takeaway for our listeners?
For me, it's the interconnectedness of everything. We started with simple examples of symmetry in nature and ended up exploring the origins and evolution of the universe. It's a reminder that there are underlying principles, hidden patterns and rules that govern it all.
It really highlights the elegance of the universe, doesn't it? The fact that these seemingly abstract mathematical concepts like symmetry have such profound implications for the way the universe works, from the tiniest particles to the largest structures.
Exactly. And it underscores the power of human curiosity and our drive to understand the world around us. We started with simple observations like the symmetry of a butterfly's wings, and through centuries of scientific inquiry, we've been able to unravel some of the universe's deepest secrets.
It is inspiring to think about the journey of discovery and how much we've learned about the universe. And yet, as we've discussed, there's still so much more to explore. Who knows what groundbreaking discoveries are just around the corner?
That's the beauty of science. It's a never-ending quest for knowledge. And the more we learn, the more we realize how much we don't know. But that's what keeps it exciting. There's always a new mystery to solve, a new challenge to overcome.
Well said. And on that note, I think we've reached the end of our deep dive into the hidden rules of the universe. It's been a wild ride full of mind-bending concepts and thought-provoking ideas.
It has been quite a journey, and I hope our listeners have gained a new appreciation for the power of symmetry and the elegance of the universe.
A huge thanks to you for guiding us through this fascinating exploration. And to our listener, thanks for sending us that awesome video and inspiring this deep dive. We hope you've enjoyed the journey.
The pleasure was all mine. Until next time, keep exploring, keep asking questions, and keep looking for those aha moments.
Because as we've learned today, the universe is full of surprises just waiting to be discovered.